This presentation is about the historical development of our current atomic model, which is called, it's kind of complex, the quantum mechanical model. There's a lot of historical discoveries and theories that led up to our use of the quantum mechanical model. The first thing that we're going to talk about is the electromagnetic spectrum. To understand the position of the electron, we must first understand light. Early in the 1920s, chemists were looking at what is called a flame test. For example, these are two elements, barium and strontium. When you put their compounds into a flame, notice how barium makes a greenish yellow color and strontium makes a reddish orange color. Why do these different elements have different chemical behavior? In other words, why do they have a different flame test, light color that is produced? Well, that's when we started looking at more at the electromagnetic spectrum. The electromagnetic spectrum is different wavelengths of energy. Notice how at the lowest energy area we have radio waves. They are so low in energy, they're around us all the time. They don't affect humans at all, but we get to listen to AM and FM frequencies to give us sound in our radio in our car. On the other end, we have gamma rays. Gamma rays are very high in energy, and when they are used as a byproduct of a nuclear explosion, they can actually cause cancer in humans because they are so high energy. In the middle of the electromagnetic spectrum, we have the visible portion, and this diagram is a little off scale because the visible spectrum is actually really small. It's only a few short wavelengths that our retina can pick up colors. On the low energy end, we have red, and on the high energy end, we have violet. And they are symbolized by this acronym Roy G. Biv. So red, orange, yellow, blue, green, blue, indigo, and violet. Those are the only colors in the electromagnetic spectrum or wavelengths that our eyes can actually see. There is an acronym to help us remember the different portions of the electromagnetic spectrum. It is Red Mustangs in Virginia use extra gas. And each letter stands for something. So radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma ray. So that can help you remember the order of the energies in the electromagnetic spectrum. The second thing that we need to understand before we can begin to comprehend where the electron is in our current atomic model is line spectra. When scientists took a flame test and they looked at it through a prism or a diffraction grating, they saw different lines occur. So for hydrogen, they saw 4 different lines when the light emitted from hydrogen was put in front of a prism or diffraction grating. For neon, they saw many lines, most of which were in the red, orange, and yellow region, with a few in the green and indigo areas. Notice how no two elements have the same line spectrum. It's like a fingerprint of a human, where no two humans have the same fingerprint. No two elements, like hydrogen and neon, they don't have the same line spectrum. They're different. Also notice how we don't see a rainbow of colors, all of Roy G. Biv. So here on the spectrum from red to violet, this is what white light or light from the sun or a light in your room would make. If you held a prism or diffraction grating up to that, you would see all of the colors of the visible spectrum. But for a light coming from an element, like hydrogen or neon, or barium or strontium from a flame test, notice how we see only certain colors. So chemists were trying to understand why we only saw certain colors. They said an element's chemical behavior, in other words, its line spectrum, is related to its electron arrangement. So we're starting to make connections between light and where the electrons are in an atom. So because hydrogen and neon don't have the same line spectrum, it's because they don't have the same electron arrangement. The third thing that we need to understand before we can comprehend where the electron is in our current atomic model is this gentleman. His name is Max Planck. He is German, and that's why his last name isn't pronounced Planck, it's Planck. He came up with a new term. He said that energy is quantized. He said that energy is quantized because only certain colors are visible in a line spectrum. So for example, when we look at hydrogen and neon, we only see certain colors. We don't see the entire realm of the visible spectrum all the way from Roy G. Biv. We only see certain aspects of that. And that's why he came up with this term, quantized. Well, what does quantized mean? It means that the electron is limited to certain energy levels and positions in the atom. So the electron cannot just be anywhere it wants to in the atom. It is limited to certain positions. An illustration of this would be a person on a staircase. Notice the person can either be here, or here, or here. And if he went downstairs, he could be here as well. He has to be on a stair. In the same way, in the atom, the electron is limited to a certain location. So if I was going to use Bohr's model of the atom to help us understand that, we have the nucleus, and then we have the electron in orbit circling the nucleus. So if we were going to use this analogy, then the electron is limited to being on this level, or this level, or this level. The electron cannot be hovering anywhere it wants to, like, for example, in between these different orbitals. It has to be fixed on a certain orbital. So just like a person cannot hover in between stairs, we're not allowed to be at that position, the electron can just not float anywhere it wants to in the atom. It has to be at a certain allowed position. The fourth thing that we have to understand to be able to comprehend our current model of the atom is Heisenberg uncertainty principle. Heisenberg was another physicist who came up with this following idea. He said that we are not allowed to know the position and momentum of the electron at the same time. Well, why did he say that? Because electrons are so small, observing their location actually changes their location. An analogy would be the following. If you were in a dark room and you needed to find a balloon, well, the room is dark. What are you going to do? Well, of course, you're going to turn on a flashlight. When you shine flashlight on a balloon, it illuminates the balloon so you can actually see where it is in the dark room. Fantastic. The light from the flashlight doesn't actually change the location of a balloon, but the electron is different. An electron and atom, if we use a certain portion of the electromagnetic spectrum to observe where it is, the energy from that portion of the electromagnetic spectrum actually changes its position. It's like shining light on an electron and going, boom, it's out of the atom. It's not like the balloon, where a shining light on the balloon doesn't change its location. Why is that the case? Well, it's because the electron is so small that it doesn't have any mass, essentially. It's so negligible. Observing its position actually changes its position. So because of that reason, we are not allowed to know where it is in the atom, going back to Heisenberg's uncertainty principle. Because electrons are so small, observing them actually changes their location. In the world, like when we have a balloon or a car, observing it doesn't move it because it has mass. But the electron is not like this balloon. The electron doesn't really have any mass, so observing it actually is going to change its location. So that leads us up to our final conclusion. Our final conclusion being that Bohr's model of the atom is not totally correct. He put electrons in very specific locations. For example, he said that the electron would be either here or here. Like, these are very, very, very specific locations. According to Heisenberg, we're not allowed to know the position or momentum, meaning the direction of travel and speed at the same time of the electron. So what model do we use today? Well, that's where we're going to go in our next lesson. We're going to talk about the quantum mechanical model and how it talks to us about a probability of where the electron is in the atom. It doesn't tell us exactly its position and momentum at the same time, but it is going to give us an idea or a probability of where the electron is in the atom.